Okay, so let's look at question 4. Here we're given the molar volume of a solid at its normal at standard conditions, which is also its melting temperature. And then we're also given the molar volume of the liquid at these conditions. And then we're also given some information of the melting temperature at a different set of conditions. In other words, we're given two sets of conditions, pressure and temperature conditions for the melting point. Right, so then we're asked to calculate the enthalpy and entropy of fusion of the solid. So it's the first time we're asked to calculate the entropy. So the only thing that we really know how to calculate entropy is the Clapeyron equation. So we can't use the Clausius-Clapeyron equation, or you can. You know how to do it. So you can calculate the enthalpy of fusion, and then you can calculate the entropy of fusion, right? Because you have the relation from it. So you can go that way around, but I want to go the way around of the Clapeyron equation because we've done 755,000 examples of the Clausius-Clapeyron equation. So I just want to do one more of using the Clapeyron equation. So what the Clapeyron equation states is that dP over dt is equal to the change in molar entropy over the change in molar volume. And then for a specific process, it can be written as dP, so for fusion, for example, so let's say we're looking at fusion, then we can write dP dt is equal to the entropy of fusion divided by the molar volume change of fusion. Right. Then for a finite change where the entropy and the molar volume is independent of the temperature change. So it's something we assume. We can assume that there is no change in these quantities at a specific temperature or during a temperature change. Then we don't have to work with the infinitesimal changes. We can approximate dP and dt by their finite changes. In other words, by delta P and by delta T. So we say this. So in other words, we then use delta P over delta T is equal to fusion entropy over fusion molar volume. Right. And we of course want to calculate the molar entropy, so that is equal to fusion molar volume change times delta P over delta T. Okay. So what is the molar volumes? We're given that of the solid and the liquid. We're looking at a fusion process. A fusion means we're going from liquid to solid, so it will be that just needs to be fusion entropy, my apologies, fusion entropy. So we're going from solid to liquid, so it will be the molar volume of so just to elaborate on what this is, so this is the molar volume of the liquid minus the molar volume of the solid, delta P over delta T. So then, yeah, and we just need to pair up the P and the T values correctly. So in other words, the molar volume of the liquid is given as 163.3 centimeter cube per mole, but we'll deal with that just now. And that of the solid is 161.0 centimeter cube per mole. But I want to work in meter cubed, so we're going to work this to meter cube by taking that, doing that conversion. So how did I do that conversion? Well, remember centimeter cube per mole can be converted easily. If we want meter and we have centimeter, how many centimeters there in a mole? In a meter? Well, there's 100. If we take, then we just need to cube it. So in other words, that gives us 10 to the power minus 6 meter. So that's how I did that conversion. Then this is times delta P. So let's take our first one as the one corresponding to 100 atmosphere. So 100 atmosphere corresponds to 351.26 Kelvin. So 100 atmosphere corresponds to 351.26 Kelvin. Okay. And then 1 atmosphere is the other boiling point, and the other melting point is 350.75 Kelvin. It is 75. Yeah, 75 Kelvin. Right, but we don't want to work in atmosphere because we're working with meter, we're working with Kelvin. So we need to work in Pascal. The conversion for atmosphere to Pascal is 1 atmosphere, or actually there is, so yeah, for every 1 atmosphere there is 101,325 Pascal. Right, that's our conversion factor. So we plug that in. Then we get a value of 45.23863 and so on. We have 3 significant figures. Yep, 3 significant figures, 1.00, 100 atmosphere. So now with 3 significant figures, so that's 45.2. We will be left with joule per Kelvin per mole. Okay. Then the enthalpy of fusion. So remember, how do we calculate enthalpy of fusion? Well, the entropy of fusion is equal to the enthalpy of fusion divided by the transition temperature, so the freezing temperature. So in other words, the enthalpy of fusion is just equal to the freezing temperature times the entropy of fusion. So our freezing temperature is 350.7 Kelvin times 45.23863 and so on joule per Kelvin per mole, which is then equal to 15867.4503 and so on joule per mole, which is then rounded off to 15.9, so 3 significant figures, kilojoule per mole. Okay, so quite a significant, high increase in both the entropy. Makes sense, going from a solid to a liquid, or actually it's from fusion, so interesting. This liquid, this solid fusion entropy is positive, so it means there's an increase in the disorder for the fusion process. Can argue why that is. So the solid is more disordered than the liquid. Interesting. Might be because the crystal structure is less ordered than the liquid structure. Anyway, and then the enthalpy is, of course, always positive, so it's an exothermic process. That's all you can really get from this. Okay, so that's how you can use the Clapeyron equation. You can of course test this with the Clausius-Clapeyron equation, and you should get the same values, but you can test that on your own. All right.